So today I'm going to be talking about the implications of interoperability. But first I'll start with something like a problem definition. I'm sure over the last few months or over the past year that you've heard a lot about blockchain interoperability. This idea that you would have projects that enable blockchains to communicate and to pass messages or tokens between them. So I'll start basically by describing why that's actually desirable. So to really begin that, I want to start with the observation that specialization breeds optimization. So when you have a solution, when you have a problem that you can specialize for, it means that you can take specific routes towards solving that problem that allow you to specify, to specialize and gain concrete performance improvements. For example, by using a better algorithm or a better data structure. If you're working in a very generalized computational system, where you're trying to solve a family of problems, you have to account for properties that apply to all of those problems. That means you can't specialize, you can't use the most efficient algorithms, you can't use the most efficient forms of data storage. So this applies to blockchains as well. If you have specialized blockchains that are meant to do a specific task, then if you can specialize them, they will be more efficient than their general counterparts. Specifically, where this would apply is for example, in the smart contract space. So as we've seen, one size doesn't really fit all. We've had a lot of different blockchains launched so far. We've got probably even more being discussed and being built right now. But different projects need different designs, particularly state machine designs. So the state of the blockchain ecosystem currently looks something like this. You have all these distinct bubbles. They don't really bump into each other. They don't talk to each other. They don't pass messages between each other. Every blockchain, more or less, that I've seen launched recently is trying to provide a new consensus algorithm, a new smart contracting platform, and a scalability solution, and everything but the kitchen sink, basically. So our feeling is that it will really streamline the development process if teams could focus on one specific aspect, do that really well, and that would interoperate with something else that does another specific aspect and does that really well. So currently we're facing a pretty fragmented landscape. So current generation blockchains can't really talk to each other. They need to go through, for example, bridges, where you have something like threshold relays. You have a trusted set of people who are allowed to ferry messages between chain A and chain B, and they have to sign off on all of those messages. So that's fine, but it doesn't really scale to many different blockchains. I mean, if you would, for example, have 10 different blockchains, and they all need to talk to each other, that means a lot of bridges if you have one from each chain to every other chain. So part of the problem is to figure out how we can do interoperability in a way where we have a fragmented landscape currently of many different chains, and then we can connect them in an efficient way. And in a trustless way as well. So what blockchains are composed of, I like to view it in two parts. So one, you have a consensus algorithm. The goal of a blockchain is really to create this global or universal agreement over some state. So a consensus algorithm does exactly that. That could be proof of work following the longest chain. It could be something like PBFT. It could be the grandpa consensus mechanism, which I'm talking about now. The goal is to give you a global agreement on some state, some history of transactions. It's actually independent from the transactions. So the transactions are the state machine. What are the changes that are actually agreed upon by the consensus algorithm? So that could be something like cryptocurrency payments, it could be smart contracts, it could be file storage commitments, it could be something like that. You know, it's a general notion. So we have a consensus algorithm and some state machine. And you put those two things together and you essentially get a blockchain. And our goal is to reduce duplication of work. So and I think these are not quite the most recent versions of the slides, but that's fine. So we reduce the duplication of work basically by abstracting out the consensus algorithm. If you can abstract out the consensus algorithm, then all of a sudden you don't need a team of researchers to build a blockchain. You've just got something sort of pre-created that gives you agreement, and all you have to figure out is what goes in that state machine slot. So as a developer, you're picking a new state machine, your new novel idea that's going to change the blockchain landscape. So one tool that you can use to do that is Parity Substrate. Essentially, this is a tool of a set of libraries that are designed for making blockchain development easier. It abstracts over common things like implementing consensus algorithms, providing network services, chain synchronization algorithm, the database. So essentially, as a team, all who's building a blockchain, if you use Parity Substrate, all you would have to do would be to build the state transition system, the state machine system of that blockchain. So our guiding design principles when coming up with an interoperability solution would be hierarchicality. I'll get to that in a second. Extensibility. So extensibility is the idea that we don't know everything that's been invented yet. I mean, we don't know what kind of scalability improvements that people are going to come up with. So you need to come up with some kind of system when you're designing an interoperability framework that's going to accommodate solutions that people build after the fact that it's deployed. So you need something very general. We want it to be developable. If you have a team who's trying to build on this interoperability framework, then they have to actually have access to the tools, the documentation, and support that makes it possible. If it's impractical to build upon, then it's not going to be very successful. That needs to scale. If you can add a lot of chains. Now, right now, the sort of bound on this is quadratic. So we're not the only team doing this, but there are many teams sort of looking into things like super quadratic sharding. And this is going to happen in a few years, but right now the limit is quadratic scalability. And of course that the system is general, that it supports all kinds of state transition systems, that it can support particularly specialized systems, and that those can communicate amongst themselves. So to describe the problem of blockchain interoperability in a few slides, or in a few sentences, you have these initially isolated chains that serve distinct purposes. Then you overlay a messaging framework between them so that those chains can actually talk to each other, and all of a sudden this opens up a lot of new possibilities for applications. And the messages have predictable properties, that the messages arrive in order. So if I'm chain A and I want to talk to chain B, if I send message 1 and then I send message 2, I want to know that message 1 is going to arrive before message 2. And you could build messaging systems that have different properties than these, but in the terms of developability, we actually think that these properties are extremely necessary for people to build interchain applications that actually make sense. And the other property that's extremely desirable is eventual receipt. That if I send a message or try to send a message to chain B from chain A, that this message will eventually be received. If you're dropping messages, then you all of a sudden have to build this whole protocol of acknowledgements and polling. If you know that the message will be received eventually, you know, the same kinds of guarantees that TCP provides over UTB, then it's a lot easier to develop this stuff. And in particular, because the cost of sending a message can often be relatively high, so you want to do that as little as possible. Only the bare minimum amount of information should be sent between chains, and if you constantly have to poll and acknowledge and see if the message actually has arrived, then that's additional overhead that we'd like to avoid. So this can get us into this situation of Turing-complete message passing, which is a bit of a problem. So if you consider a situation where chain A can send a message that makes chain B send 2 messages that each make chain A send 2 messages, you sort of end up in this situation of exponential blowup. And that's just a trivial case. So this is roughly analogous to the halting problem in computing. It's probably identical to it. You can prove that actually. But this means that we have to basically impose a fee structure on messaging. messaging can't be free because with those requirements, messaging can lead to Turing-complete computation. And this is the same insight that Ethereum had with Turing-complete computation. You have to charge gas for computation because it can end up into Turing-complete infinite loops. So one challenge that we face in an interoperability framework is the challenge of attacking weak chains. So in economics, everything has a price. So let's imagine that we have two chains and that there's a bridge between them. So the yellow box around each chain sort of denotes the finalized portion of the chain. I'm sure many of you have heard the term finality before, or even absolute finality. I'm here to assure you that finality is not final, and that finality can always be reverted for a price. So let's say that chain 1 has $3 million of security on the finalized chain, that it would take $3 million to revert the finalized chain, and chain 2 has $10 million of security. So if I was to pass a message from this green block in chain 1 to another block in chain 2, that's basically a cause leading to an effect in chain 2. But then chain 1 were attacked and reverted, and that green block that was finalized has been reverted and is no longer in the most commonly accepted finalized chain. Then all of a sudden, you have an effect on chain 2 without a cause on chain 1. So for example, if that effect was, if the cause and effect were a token transfer, that I transferred $1 million of tokens from chain 1 to chain 2, then I would be in big trouble because all of a sudden we've double spent them because now they still exist on chain 1, but they've also been minted on chain 2. So the conclusion to draw from this is that a network of interoperable chains can only be as strong as its weakest link if you connect them with bridges. So what Polkadot does is slightly different. Polkadot sort of unites all the chains under a relay chain. The relay chain is a special purpose chain that provides consensus for all of those chains in lockstep. What that means is that you can't revert one chain without reverting all the other chains. They have pooled security, which means that the weaker chains are protected by the stronger ones. But the network effect makes the cost worth it. So to see an example of this, I guess that slide isn't there. So you won't see an example of that, but I'm going to talk about this. So to talk a bit about scalability versus interoperability. So far I've talked mostly about interoperability, which is the passing of messages between chains, but it's actually very closely linked to scalability. So let's take a step back and think about sort of the articulation of the problem that I've put forward so far. Now our issue right now is that blockchains aren't scaling. So you have a blockchain that accommodates 10 transactions per second. So one solution to increase absolute scalability would just be add more blockchains. Like let's run 5 Ethereums instead of 1. Let's run 10 Bitcoins, right? So this adds more transactions per second. But what you lose out on is the network effect. And the network effect actually adds a lot of value. So the idea of an interoperability framework is you can run 5 blockchains instead of 1. You can run 20 blockchains instead of 1. But you can still have the network effect cross-chain. Now, the question is, how do you do that in a way that maintains the security properties of those chains? And the other thing that you typically wonder is, how to keep the security, and also how do you prevent double spends and that sort of thing. My slide is back. This is an example of the Polkadot relay chain. So basically, coming back to that, we have all these different chains which are specialized, and they're united under a interoperability framework. So all of a sudden, instead of one blockchain that's supposed to handle all the transactions, you have many different chains that are each handling their own transactions. And they're united under the relay chain, which is providing consensus for all of them, but also providing messages between them. And one interesting thing to note in this diagram is that notion of hierarchicality. So one of the chains in this diagram is actually another relay chain with another relay chain. So you can have this sort of tree of chains. And this is what I mean by the notion of hierarchicality. If you want to speak about scalability, a lot of the time, again, you want to specialize to localities of region or localities of application. So when you can create a group of chains that are all doing the same thing, or all exist perhaps in geographical proximity to each other, you can achieve sort of a relative finality for transactions within that cluster or within that subtree faster than you can with the whole. And that's why hierarchicality is useful. So I'll spend the last section of this talk, depending on how much time I have, mostly to discuss what interoperability would mean for applications. So basically, as an application developer, what does it mean to develop an application on a network of interoperating chains? So one is, again, this principle of locality. If you have many moving parts in a DApp, you want to minimize the traffic between chains because this has high overhead and perhaps high latency. So keeping portions of the on-chain application logic localized near or on the chains it interacts with most is really important. So for example, you could have a lot of computation happening on chain A, but periodically you have to send a message over to chain B or chain C to get something done or to interact with some other DApp. Asynchronous communication, again, is fairly expensive. Synchronous communication is easier, so that's basically you would make a smart contract call, and then your code blocks until that call returns. Whereas asynchronous communication is, I send out a contract call, but I have to keep working, and I don't know when the result is going to come back. Synchronous communication is easier to reason about, but it's not always possible. That would be, for example, within a smart contract chain, synchronous communication would occur, and between smart contract chains, asynchronous communication would occur. So one example of an application would be a decentralized exchange. So the DEX wants, as a requirement perhaps, for users to be able to trade directly from their wallets without having to lock money up, so that you can essentially overbid the amount of money you put down. So a DEX chain can automate these cross-chain transfers. So you have a DEX chain, you have tokens living on two other chains, and the DEX chain sort of pulls in the tokens to its local chain, sees if those succeeds. If they both succeed, it does the swap. Otherwise, it sends the 1 or 0 sides of the trade that it got back. So there's sort of an example of that happening. The DEX attempts the transfer. If it fails on either side, it reverts to step 1. So one other option would be to actually embed a decentralized exchange module into each chain that might want to do trading between other chains. And then you would have essentially trades happening locally within a chain, but you have these market makers, big whales basically, who move the collateral around behind the scenes between the chains. Another example that I think personally is really interesting is the IoT chain. So, and I don't have much time, so I'll wrap this up really quick, but the adoption is not really going to come unless you have stuff happening behind the scenes, and I think IoT is a really good option for that. So the idea is that you have these LoRaWAN devices, devices that really can't receive much data, and they can't interpret complex proofs of execution from a chain. So rather you have a parachain that can receive messages from other parachains. And light clients know how to interpret the receipt of messages on that parachain. And that would be very compact. So then you can send an IoT message to an IoT device that's a compact proof of finality of the relay chain, plus the proof that a message has been received by this IoT chain. And that would allow IoT devices to basically interpret events that have happened on anywhere in the Polkadot network, which is quite promising. And I'm going to skip that, and skip that, and skip that. So thank you very much. I'm afraid I don't have time for questions. But please come talk to me afterwards, and I can discuss something further. Thank you.